Good morning, friends. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. In March this year, our company completed 25 years in fired heater business in the US. We are conducting free fired heater training webinars this year as a part of our Silver Jubilee celebrations. So welcome to our session on ethylene cracking furnaces. I welcome you all. We have received more than 160 registrations today, and I thank you for all your time and interest. So today we are going to be doing an interactive webinar. So you will be as involved as I am. You will be responding and acting into the giving your feedback to us all the time. So if you have any question, you can use the webinar platform to send it to us. So we will go straight into the Kahoot. So we are planning to conduct this webinar in 4 parts. Today is the first session, and we want to get your feedback, comments, suggestions on improving our webinar so that it will be more effective. So let us start, and here is a simple quiz for you. We are going to be talking about ethylene for next 90 minutes. So what is the chemical formula of ethylene? I think it would be an excellent time to refresh our basics of organic chemistry that we all studied in high school. Ethylene is one of the important petrochemicals produced worldwide. It gained prominence especially after World War II. Before ethylene, acetylene used to be used as a base. Ethylene has no direct end uses and has been used exclusively as a building block in petrochemical industries. US refiners started separating it from the refinery waste gases and then later on started producing it from ethane, which was obtained from the byproducts. So most of you got it right. The formula of ethylene is C2H4. It has 2 atoms of carbon and 4 atoms of hydrogen. The formula is C2H4. Thank you very much. Let's move on to the next question. So ethylene has carbon to carbon bonding between the 2 atoms. So I want to find out from you whether it is single bond, double bond, triple bond, or quad bond. Carbon is one of the few elements that can have long chains of its own. It can have single bond like alkanes, and some examples are ethane, propane. They are the feed for ethylene cracking. Well, very good. Most of you got it right. Carbon to carbon double bond compounds are known as ethylene and propylene. They are the desirable products. Carbon to carbon triple bond is known as alkynes, such as acetylene. Multiple bonds are generally a lot more stronger. Single bond has a dissociation energy of 90 kilocals per mole, while double and triple bonds have dissociation energies of 174 and 230 kilocalorie per mole. So let's move on. Let's summarize. Ethylene, the chemical formula is C2H4. Its technical name is actually ethene as per IUPAC. Molecular weight is 28.5. It's a colorless flammable gas with sweet musky odor. As I said, it's very reactive and combines with other chemicals easily. So it's a very important building block for the petrochemical industry. So let me start spend a little time on myself. I want to introduce you. If you don't know me, my name is Ashutosh Garg. I'm a chemical engineer. I passed out of IIT Kanpur in 1974. Since 1976, I've been working on fired heaters and combustion systems. I have worked in KT India, Engineers India, and KTI Corporation in US. And I've been working at furnace improvements from 1996 onwards, revamping heaters and improving their performance for past 25 years. So we started furnace improvements in 1996 with a mission to improve the performance of existing fired heaters. Since then, we are focused on revamping fired heaters and increasing their capacity, run length, and efficiency. We have 3 patents on improving the performance of fired heaters. We have a contrarian approach, and we have been constantly challenging the conventional wisdom and worked on new approaches to solving problems. We have 3 offices and a team of 35 engineers and designers. We can take projects on turnkey basis. We are one of the few heater companies with its own CFD modeling office. I want to take this opportunity to thank all our customers for their business and support, and that is how we have made this webinar possible. I want to start thanking out by our New Delhi team of process engineers for working hard for the past 6 weeks. Our team of process, mechanical designers, and engineers have been working on putting this presentation together. Thanks to all the team members for their hard work. All material that has been presented here today is from literature, and no proprietary information has been disclosed in this presentation. I just want to make it clear that there is plenty of information available in literature, and that's what we have used today for our webinar. So we did this course with another company in 2017 on cracking heaters. But this time what we did was we asked all our participants to provide us 3 topics and concerns they would like to see covered in our webinar. I want to let you know we had a tremendous response, and almost 150 of you responded with the questions, and that gave us 300 topics to be covered. We want to cover what concerns you. So we have thrown out our old course material, and we will be covering your comments and topics in the next 3 sessions. We will also post replies to all your technical queries on our Facebook, LinkedIn, and website. Please keep us sending more questions at us, and we will try to answer them. So I want to talk a little bit about cracking furnaces or any fired heaters. They all have 2 sides. Cracking furnaces also have 2 sides. One is what is happening inside the tubes, the radiant tubes, and that is reaction kinetics, and that is a proprietary technology of 4 or 5 companies in the world. We cannot help you there. But the other side is the flue gas side or the fire side. And it is the fire side in all fired heaters which control the heat transfer. So we have a lot of experience in dealing with fire side issues, fire side problems, and we can help you with any and all fire side, whether it is concerning burners, whether it is concerning fan, burners, combustion, refractory. In fact, if you look at all the feedback what we have received, majority of the feedback is concerning the fire side. You know, flame impingement, coil bowing, flashback, heat distribution, high tube metal temperatures, run length issues, tube failures. All these things are related to the fire side, and we would be able to help you with all these problems. In our experience, flame impingement is one of the most common problems in fire heaters, and we can definitely help you improve your burner's flames. Look at all these questions, and these are all feedback from what we have received from you, like low efficiency, NOx emissions, CO2 emissions, high shell temperature, hotspots, refractory failures, fans, burner tip clogging. All these issues are on the fire side. So we should be able to help you with all these issues, and as I said, the only thing what we don't do is the reaction kinetics inside the tube. So that's the thing we cannot do, but everything else we can help you. And you look at all these things, typical failures, flame patterns, all those things, we will try to help you with the operational issues, questions, your license. I want to make it very, very simple. We can help you with the draft if you're having draft limitations, if we can help you with the ceramic fiber, CO2 emissions, greenhouse gas emissions. If you want to reduce greenhouse gas emissions from your furnaces, you want to reduce NOx emissions from your furnaces, we can help you there. So we got tons and tons of questions actually. I don't know whether we can cover all these questions in the next 3 sessions, but we will try. And as I said, we will put them in the Facebook, LinkedIn website. Furnace operation and control, furnace startup, burner cleaning, CO2 emissions, draft calculations. Most of those things are concerning fire side, and we should be able to help you. Give us a chance to look at your furnaces and improve the performance. So again, let's get your feedback. What type of feedstock are you using in your cracking furnaces, whether you're using gas, liquid, or liquid and gas both. So all right, so majority of people are using gas, 42% of the people, 20% are using liquid and gas feedstocks. Some are using liquid only, 5% of the people are using liquid, 21% are using liquid and gas both. Now we do have some people, participants who don't have any cracking furnaces, so I just want to get feedback over here. Thank you for your feedback. Let's move on. What type of gaseous feedstock is used in your cracking furnace? There are choices of LPG, ethane, NGL, and propane. So these are the 4 typical feedstocks which are used in the cracking furnaces. Well, most of us are using ethane, and you will see because in US it is available in plenty, especially because of the shale gas revolution. And there are some people who are using LPG and NGL. Well, thanks for the response. If you are on the liquid side, what type of liquid feedstock is used in your ethylene cracking furnaces. The choices are naphtha, hydrocracking residue, gas oil, or other refinery heavy oil products. Well, majority of you are using naphtha. Naphtha is an important feedstock for cracking. Thank you again. So if you look at the feedstocks for the cracking furnaces, we are looking at gaseous feedstocks, which are basically ethane, propane, butane, LPG, and NGL is a mixture of ethane, propane, and butane, or the liquid, which is naphtha, gas oils, hydrocracking residue, other refinery heavy fuel oil products. Just want to let you know that there is a effort in the industry or trend in the industry to use crude and crack the crude straight and get into different products, including ethylene. So they are thinking of even cracking crude directly. So just to give you a feedback or information, you need 3 times naphtha as compared to ethane for the same ethylene production. So that's generally the thumb rule. So naphtha is a very important liquid feedstock for most of the cracking furnaces. It is a mixture of more than 100 hydrocarbons, boiling range in the range of 85 to 390 degree Fahrenheit. Typically, naphtha, which is ranging from 85 to 200, is called light naphtha. 200 to 390 is called heavy naphtha. So, and full range naphtha is between 85 to 390. Naphtha can be also analyzed because on the density, also based on the content of paraffin, isoalkanes, olefins, naphthenes, and aromatics. It's called Piona analysis. So the feedstock has a potential for big range of products, what can be achieved. So this is a analysis of 2016 and 2021. World is using about 50-50 naphtha and ethane. The trend is more towards ethane in US and more towards naphtha in Asia and Europe. But even LPG is holding steady at about 14%, others are about 8%. Also, ethylene process is very energy intensive, and we generate 2 kg of carbon dioxide gas for each kg of ethylene produced. So that's another thing to take notice on. Well, here is a question for you. What is the total worldwide how much ethylene is produced every year? Ethylene is used in large variety of downstream sectors such as production of polyethylene, ethylene oxide, polyester, PVC, EDC, ethyl benzene. So, well, most of you got it right. It is almost touching 200 million tons per annum. So, Asia Pacific region has the largest ethylene production capacity now, and the worldwide production is continuously increasing. So there are almost 315 ethylene plants throughout the whole world. And this is just an estimate. My estimate is about there are 3,000 ethylene cracking furnaces. There are 117 companies in 32 countries who are producing ethylene. The largest companies are BASF, Dow Chemicals, ExxonMobil, Lyondell, Ineos, Sabic, Formosa Plastics, DuPont, and approximate growth is about 5 to 6% per annum. You can see over here in 2005, we had a worldwide capacity of 107 million tons per annum. And now in 20 years, it will be almost 3 times, 283. I mean, right now it is about 2019, it was 192. So it's almost like 5 to 6% growth per annum. And so lot of growth in plastics. I mean, you can see plastics are entering every sphere of our life. So, and to make those plastics, we need these ethylene or polyethylene in our plant. So generally, plants will have a multiple of cracking furnaces, and that is because of variation in feed, variation in run length. I mean, and because of run length, you can have a different this thing. So just want to get a feedback as to how many furnaces are there in your plant. On an average, about 8 to 10 ethylene cracking furnaces are there. So we have a wide range actually. Anywhere you can see it's uniformly split. I mean 3 to 5 is there because and rest is almost evenly split. So we have the whole range of ethylene furnaces in our plants, chemical plants. So what is the production capacity of your ethylene cracking furnaces? So the production can be anywhere between 50,000 metric ton per annum to more than 150 or 200,000 tons per annum. If it's around 50,000, then it's a very old, small cracking furnace. And if it is 200,000, then it is a new high intensity cracking furnace. So most of the people have between 100 to 150 metric tons per annum ethylene capacity, which sounds right. Nobody has 50,000 metric tons per annum. These were the old furnaces which were built in, I think, around 1950s or maybe even earlier. And some have between 50 to 100,000 metric tons per annum. These could be small furnaces built in India, maybe around 1960s or 70s. So thank you again for your feedback. So we want to find out what is the final product from your ethylene plant, because ethylene, nobody produces ethylene. They are always producing something else. Ethyl benzene is a precursor to styrene. Polyvinyl chloride is a plastic. LAB is a detergent. So, and polyethylene is a plastic again. So lots and lots of products. So most of the people are producing polyethylene or PVC, surprising anyway, very good. We have a good response here. Thank you. So if you look at the ethylene, there are lots and lots of uses, starting with polyethylene, ethanol, ethylene oxide, vinyl acetate, 1,2-chloroethylene. Then you can make ethylene glycols, glycol ethers, ethoxylates, Vinyl chloride can go into polyvinyl chloride, engine coolers, polyesters. We haven't listed polystyrene here. We have not listed linear alkyl benzene. So lots and lots of uses are there for the ethylene, and it's growing worldwide. So our feedstock is gas and our product is ethylene. So how do we get to that reaction? What happens? What is the process, or what is pyrolysis? Uh, well, almost everybody got it right. Pyrolysis is decomposition at high temperature. Uh, pyro means, it's a Greek word. Pyro means fire, and lysis means breaking or losing. So pyrolysis is breaking of molecules with heat. It is defined as thermal decomposition of organic materials at elevated temperatures in the absence of oxygen. It is also called thermal cracking. Uh, it's mostly done in the presence of steam. Dilution steam, although does not take any part in the chemical reaction, but it does help in improving the yield of ethylene by reducing partial pressure, as well as in coking. So it does help, I mean. So that is the basic pyrolysis, what is taking place inside the radiant coils where the reaction is taking place. So we want to see what are we feeding to our ethylene furnaces, or what temperature are we feeding the gas to or liquid to our ethylene cracking furnaces. We have 4 temperature ranges over here. Most of the feedstock, so it's ranging all over the place. Generally, you want to feed the coldest so that you can recover the most heat uh, from your furnaces or hot flue gases. Typical temperature is 100 to 250 degrees for the gas furnaces. People who are heating more than 400, maybe they are having vaporized naphtha entering into the system. So that's a very big range here. There is somebody who is feeding at less than 100 degrees. Thank you. Let's talk about the outlet temperature. What is the feed outlet temperature from the cracking furnaces? So pyrolysis reactions take place at high temperatures. So feed outlet temperature could be very high, depending on the feedstock. Range is from 1400 to 1600 degrees F. Okay, so we have range all over the place, evenly split. Ones which are in the high temperature zones is like ethane cracking. I think the low is around naphtha cracking. So, but thank you again for the response. And you can see how much this is one of the hottest furnaces. I don't think we go to these temperatures of 1600 in any other furnaces. So very, very critical. And most of this high temperature has been possible because of advances in the metallurgy. By better alloys, we are able to get into uh, higher temperature zones. So metallurgy has really, really helped. So this is an easy quiz for you. Is ethylene cracking reaction endothermic or exothermic? In exothermic reactions, energy is released. In case of endothermic reactions, you need heat input. So majority of you got it right. It is an endothermic reaction. That means heat is needed, and that's why we have a cracking furnace. We have a furnace where we are providing heat. So it's an endothermic reaction. The correct answer is ethylene cracking requires energy. It's approximately about 2100 BTUs per pound. That is the energy required in cracking furnaces. And that energy is provided by the fuel which we fire in the furnaces. That's the energy that is provided. So in the pyrolysis or cracking reactions, longer hydrocarbon chains are cracked into smaller molecules. Cracking reaction requires high energy rates for the reaction to take place. This energy is provided in the form of the heat. The hydrocarbon feed can be in the form of liquid or gas, but pyrolysis reaction is basically a gas phase reaction, and we mix steam with the feed to improve the yield, and the outlet products are cooled quickly. That's basically how the pyrolysis or cracking works. So if you think about cracking, we can write a very simple reaction, and that simple reaction is you take ethane, you remove two atoms of hydrogen, and you get ethylene and hydrogen. So one molecule is divided into two molecules. So that is a very simple reaction which can be happening. But what we really find is it is a lot more complicated, and there are lots of reactions which are happening. So the cracking heater coil is acting like a tubular reactor with reactions taking place inside the coil. So when we do cracking, we get a lot of products, and these are complex reactions, and thousands of chain reactions take place. Professor Rice came up with a theory in 1930s about explaining how these reactions are taking place. How do we get ethylene, olefins, diolefins, methane, acetylene, etc.? And what is the reaction mechanism? So he came up with a three-step process. And what first section is, one reaction as we showed you is ethane cracking into ethylene and hydrogen, but the other reactions are which produce methane, acetylene, butane, butene, toluenes, all these. So he came up with a three-step theory of initiation, propagation, and termination reactions, and explained the reactions. And this is true even for the low temperature cracking. For high severity cracking, this theory does not hold good, and it becomes even more complicated. So let us talk about the first reaction, which is called the initiation reaction, how the cracking gets initiated. And here what is happening is ethane is breaking into two compounds which are called radicals. And here it is breaking into two methyl radicals. And that is what is happening to other molecules also. If we have a propane or if we have a butane, they are also going through the same process of generating radicals. So we want to ask you here, what is a radical? What is a radical in the chemistry? If you have selected so radicals are atoms or molecules with oh, you're still answering. Okay. I think all of you got it correct. Radicals are atoms or molecules with unpaired electrons. Radicals are highly chemical reactive, and most radicals have very short life actually. So radicals are active species that govern thermal cracking reactions. Prominent radicals formed during pyrolysis furnaces are ethyl, methyl, and hydrogen radicals. So let's see what is happening next actually. So now we call it a propagation reaction. That is the second step. And here the methyl radical, CH3, reacts with ethane, C2H6, to form methane and ethyl radical. So you can see one reaction which is taking place. There are several reactions taking place. So propagation reaction consists of radicals reacting with paraffin molecules to generate more radicals. That's what is kind of happening, So this is one radical. The second one is ethyl radical generating ethene or ethylene and generating a hydrogen radical. And that hydrogen reacts with ethane to make hydrogen molecule and produce ethyl radical. So you can see all these complex reactions are taking place, and propagation reactions consist of radical decomposition and the addition. That's typically all these propagation reactions are taking place. The chemistry is complicated here. Propagation reactions, depending on what reactions are happening. If 4 and 5 are happening, we will get ethylene and hydrogen. If 3, 4, and 5 are happening, we will get methane, ethylene, and hydrogen. And if one radical reacts with the other, so then the reaction starts terminating. So you can see over here how the reactions are taking place. And here we are only talking of ethane, one, In case of propane, it becomes even more complicated. In case of naphtha, it becomes even more complicated because we have lots and lots of compounds. So it is a complicated reaction which is taking place. We are only talking of simple issues here. And one thing what we are seeing over here is if you got two hydrogen radicals, now we are in the termination stage of the reaction. So that is the last step of the reaction. And here radicals are reacting with each other and making compounds like hydrogen radicals combine to make hydrogen, methyl radical combine with hydrogen to make methane, ethyl combine with hydrogen to make ethane, and then ethyl and methyl radicals combine to make propane. So you can see there are lots and lots of reactions taking place. And when we have two ethyl radicals, they combine to form butane. So we just got into 10 reactions, a series of 10 reactions on propane only. Sorry, ethane. On ethane feed, we have got a series of 10 reactions explaining initiation, propagation, and termination, and explaining formation of some of the compounds. It's still not explaining the other compounds which are being formed over there in the product. So then we came up with secondary theory. And the second theory is that there are two sets of reactions which are taking place. In the primary reactions, we are forming ethylene, propylene, acetylene, hydrogen, and methane. And then in the secondary reactions, we are forming C4 products, butane, butenes, butylines, pentane, pentenes, C6 aromatics, and C7 heavier products. And the way to stop these reactions is we need to cool them quickly and separate them in the cold section. So all these reactions which you saw that the hydrocarbons were acting on their own actually. And what engineers or the scientists found was that when they were cracking hydrocarbons alone, they were producing a lot of coke and other products. So then they said, okay, let us introduce steam. Let us inject dilution steam in the cracking process. And tell us what will happen when you put dilution steam. What role does it play? So most of you got it correct. Steam is playing two important roles. One is reducing the hydrocarbon partial pressure. And if you have seen the reactions taking place, the lower hydrocarbon partial pressure favors the formation of ethylene and propylene and cracking reactions. So that is one benefit of injecting steam, is to lower this thing. And second is when you put steam, it increases the velocity and reduces coking in the tubes. And also it reacts with carbon or the heavies to make water gas reaction, which is CO2 plus C goes into CO2 plus water, hydrogen. So it makes a lot of difference. It improves the olefin yield, results in better operation. So since that time, we have been injecting steam in the cracking process. That is the benefit of injecting steam. So dilution steam role is lowers the partial pressure for reacting hydrocarbons, thereby enhancing olefin yield. It is used for final vaporization of liquid feed also, and reduces tendency to deposit and form coke by gasification reaction. So that's basically some of the benefits of steam. So we want to ask you, all the operating folks, what is the ratio of dilution steam to hydrocarbon being used in your furnace? How much steam you are putting in your furnace? If you have a gaseous feed, you will be putting lower quantity of steam. If you have a liquid feed, you would be putting higher quantity of steam. That is generally the break. So thank you for your response. Most of the people are putting 0.35 to 0.5. So that means they are processing gaseous feedstocks. So dilution steam to hydrocarbon weight ratio, if you have ethane feed, you will be doing around 0.25 to 0.35. If you have butane, 0.4 to 0.45. In the liquid cracking, you will be, if you have naphtha as a feedstock, 0.4 to 0.5. Or if you have a heavy stock, you may go up to 0.7 to 0.85. It also depends on the cracking severity and the design of cracking coils. I think my guess is most of the operators end up putting more steam into their coils as it really helps them. So if they have steam available, they tend to put more actually. So how do we check what is happening? Because cracking furnace has one important role, that it is cracking the feed. So how do we measure our success, or our how much are we able to crack our feed into ethylene? So for the gas feedstocks, the industry standard is conversion. How much of my feedstock got converted into the products? So what I'm doing is I'm taking the feedstock concentration minus the whatever is not converted divided by the whatever I fed. So if I'm putting 100 kgs of ethane, how much ethane is being left out in the process? And that kind of gives us the conversion actually. It is very difficult to get full conversion of any component during cracking, but if you look at ethane, uh, typically you will get around 65% of conversion, 65 on mass basis. And you can see on a different, this is with 0.3 pounds of steam per pound of feed, and we are giving it at different residence times. And what one thing which is constant is the unreacted ethane is almost at about 35%. That's basically uh, the conversion, So 65% gets converted, 35% has to be recycled. Also, if you are looking at something over here, you can see uh, from 0.46 residence time, when we reduce the residence time to 0.11, we get almost like 1.5 to 2% better yield of ethylene. So these are some of the things. That's why industry has moved to lower residence time. We will cover this in our next class, more on the residence time. It is, in case of propane, it is still the similar thing, but propane gets converted almost like 90% of conversion takes place in case of propane. Uh, Although the ethylene is somewhere the same, around 37%, so, but we get a lot more propylene with the uh, ethane propane conversion. The unreaction is, if you look it over here, is still around 10%. So you get about 10% unreacted propane. So 90% conversion is uh, typically possible with the propane feed. So here we are comparing yields of ethane versus naphtha, and you can see over here, based on the mass percentage, ethane is giving you 52% ethylene, and naphtha is giving you only about half actually. So much lower ethylene is being produced when you crack naphtha on pound-to-pound basis. And naphtha cracking also is generating a lot of heavies. You can see over here. So it's a very different product slate, and naphtha cracking plants are a lot more complicated because we are having a lot more product. So the investment is higher substantially. In case of liquid feedstocks, the industry standard is little different. They look at the ratio of propylene to ethylene on the weight basis, or ratio of methane to propylene. Those are the two yardsticks they have developed for measuring the success of your cracking, that is propylene to ethylene or methane to propylene. And basically they say it is MT plus C, where T is the temperature, and that is what is accepted in the industry. These are the yields from low severity naphtha. This thing, again, you can see how we get only about 25% ethylene and 16%, 17% propylene, and then this is butylene. So it's a very different situation here when you crack naphtha. So okay, low pressure. Most of you got it right. Low pressure definitely helps. Olefin yield is increased as the partial pressure is maintained low through the cracking coil. Since most of the secondary products result from reactions in which the cracking molecules decreases, number of molecules decrease, increasing the pressure favors the secondary products. If a furnace coil outlet pressure should be maintained as low as possible. Typical pressure in the industry is anywhere between 8 psi to 8 psig to 20 psig. That's typically this thing. So let's move on. Let's talk about the temperature now. What outlet temperature is good for? Well, almost everybody got it right. High temperature, because it's an endothermic reaction. Endothermic means it requires heat. So as we increase the heat input, a higher temperature, we will have more reaction going towards the right, toward favoring the formation of more products. So generally, it's the tube metallurgy which limits us on the temperature. I mean, we would like to go even higher on the temperature, but the tube metallurgy kind of limits us. So that's basically what we are limited by, but high temperature favors the more ethylene. So this is another one. This is the effect of residence time on production of ethylene. I think so. Low residence time, yes, low residence time leads to formation of more ethylene. And also, when we say low residence time, it has helped us in reducing the size of furnaces or reducing the size of the coils. And that is one reason why we can have furnaces as high as 200. One furnace can handle now 200,000 tons per annum of ethylene, or even higher. Actually, we are building mega furnaces. And one of the parameters which is driving those mega furnaces is lower residence time, leading to more ethylene. Like the flux is much, much higher in radiant heat transfer intensity is much, much higher than what is there with the higher residence time furnaces. So that's where the industry is going. So let's look at the interactive parameters. What we have hydraulic limitations like what is the geometry, coke formation, pressure drop, hydrocarbon partial pressure profile. These come under the hydraulic. Then on the thermal side, we have the radiant heat flux, tube metal temperature, coke resistance, and the tube metal temperature profile. And on the kinetic side, we have the reactant properties, residence time, conversion, and coking rate. So you can see pyrolysis of hydrocarbons is dependent on so many parameters, and we can, it becomes like a very, very complex computer analysis. That's what can only predict what you are going to be producing from inside of those coils. So let's talk about the feed outlet temperature. The lower temperature favors the oligomerization reactions involving in formation of secondary products. Therefore, we try to apply special temperature profiles along the cracking coil toward long residence time at low temperatures. We try to heat it very quickly, and the temperature and pressure profiles are optimized along the radiant coils to maximize the yield of valuable products. One side we have the residence time, the temperature profile, and that is kind of leading to the severity of the reaction. Higher cracking temperature favors the production of ethylene and benzene. Lower cracking temperature favors higher amount of propylene, butane, butenes, and liquid products. Now, the downside of higher cracking temperature is it leads to rapid coking rate. So that's another thing. So run length goes down. The furnace run length goes down as the temperature is increased. So that's a penalty we have to pay. The other temperature problem with higher temperature is it leads to carburization and short tube life. So in a lot of plants, you have to change your coil maybe every 3, 4, 5 years. Carburization is a process where you absorb tube material starts absorbing carbon, and then it leads to brittle failure, metal dusting, and loss of material. So one thing what we have to do is to cool the flue gases now so that we don't get any undesired products. That's one way of cooling the products quickly from the exit of the cracking furnace. And we do that with, okay, so it's evenly split. No, everybody is trying to cool it as low as possible. Some are cooling to 850, some are cooling to, most of the people are cooling to 750. So it's typically, we want to cool it immediately or basically quench it using high pressure boiler feed water and generating steam in these special exchangers, which are called transfer line exchangers. So anywhere the radiant coil outlet temperature could be anywhere between 1400 to 1650, and we cool it down to 700 to 850 to avoid product loss by secondary reactions, and that is accomplished in this transfer line exchangers. There is a lot of science and a lot of engineering and a lot of development in these exchangers, complicated piece of equipment, but they generate high pressure superheated steam. These exchangers may be double pipe or multiple pipe. We are showing one over here. So if you want to see, there are what parameters affect the yield of ethylene. Basically, it's a feedstock quality, residence time in radiant section, partial pressure of hydrocarbon in feed outlet temperature, and time taken for quenching from products of the radiant oil. So if we want to optimize it, these are the factors which we need to kind of, or designers take into account for maximizing the production of ethylene. So ethylene, as we told you, ethylene crackers, whether you are processing ethane or naphtha, are very high energy intensive process. And you're almost processing absorbed duty is almost like 2.7 million BTU per 1,000 pounds of feed in case of ethane and 2.2 million BTU per 1,000 pound of feed in case of naphtha. And for a million pounds per annum cracker, you are looking at almost a heat duty of 909 million BTUs per hour. And similarly, in case of naphtha, it's even 30% higher for the same capacity, 1.227. So now the question is, how are we providing this energy? We have been talking about cracking, endothermic reaction, and how are we providing the energy? And the answer comes from the firing of the fuel, firing the fuel gas or liquid fuels, naphtha, like in your furnaces, because combustion is the only process which generates hot enough flue gases where we can transfer the heat from the flue gases to the coil or to this feed inside, which is inside the coil, because we are looking at 1500 degrees F temperature. So that's typically we can achieve only by hot flue gases. So we are firing fuel. So let's look at the heat requirement. So basically the heat requirement can be split into three portions. The first is you want to heat the feedstock up to the reaction temperature, and you're doing it mostly in the partially in the convection section and partially in the radiant section. So you typically crossover temperature is around 1100 degrees F. So you want to heat the feed, which may be coming at 100, 200, 300 degrees, all the way to 1100 degrees. You also have to heat the steam, what you are putting in this one. And then you want to heat the feedstock to the reaction temperature, which typically starts at around 1300 degrees F. You want to start, you see in the reaction, and then it comes the endothermic heat of cracking actually. So that is the reaction heat. So that we have to provide before we get out the product. And if you are processing naphtha, then you had to vaporize the naphtha. So that is another heat needed actually, which is latent heat of vaporization. So you can see ethylene cracking is a highly energy intensive operation. Ethane has the highest endothermic heat of cracking at 1150 kilocalories per kg. So we need to provide a lot of heat. So let us see what units do you use to quantify the heat energy. Different parts of the world are using different systems. So So if you are in the US or North America, you are using millions BTUs. If you are in India, you are using million kilocalories. If you are elsewhere, I think you are using either gigajoules or megawatts. They are all the units for measuring heat. Heat is a form of energy, and it can only be transferred from one source to another. In case of fuels have chemical energy inside those molecules, and when we have combustion taking place, we convert that into thermal energy. So I want to ask you something. Okay, I think we. So flames are very, very hot. You can see the ranges what we have given over here. Although there is a typo here, they should be 3,500 to 4,000 degrees F, the first one in the red. I apologize. So most of you got it right. I mean, even if you got 3,000 to 3,500, that may be the flame temperature with excess air. But typically flames of the point I want to make is flames are very, very hot. They are anywhere in excess of 3,000. Theoretical flame temperature, which cannot be measured, is generally in the order of 3,500 to 4,000. Ethylene has a flame temperature of 4,200 degrees F if you burn ethylene. So flame temperatures are very, very hot. And what I want to tell over here is imagine flame touching your tubes. When we talk of flame impingement, we are talking of flame touching your tubes. And imagine if you have anything with 4,000 degrees F or 3,000 degrees F touching your tube is doomed. So that is why flame impingement is one of the biggest problems in our industry. Any heater you take, you will see flame impingement is leading to lots and lots of problems. So we generate these flue gases at about 3,500 to 4,000 degrees F, and then we want to ask you what is that flue gas temperature in the firebox. This is also known as bridge wall temperature, the flue gas temperature leaving the radiant section after giving out the heat. And so typically, if you have a high severity furnace or low residence time furnace, you will be in the range of 2,000 to 2,200 degrees. If you have a lower one, it could be in the range of 1,800 to 2,000 degrees. You know, typically the flue gas temperature is very, very hot. First thing is it has to be higher than the tube metal temperature in the radiant section or the flue gas, I mean the feed outlet temperature, which could be around 1,600 degrees F. So here is a want to find out what is the flue gas temperature leaving the stack of your cracking furnace, leaving the convection section or leaving the ID fan or leaving the stack. What well, most of the people have their 40% of the people have very high efficiency furnace, which is almost like state of the art between 250 to 300. Those are the high efficiencies. People who have got more than 600 degrees need help. They can contact us. We can improve their efficiency. Even with people with 400 to 600, it looks like there is a scope for improving the efficiency of the furnaces. So do you have a combustion air preheater in your cracking furnace? Most of the people don't have it, but it could be something nice to have, as a combustion air preheater improves the flame patterns in the furnaces. Well, we have a 50-50 split. 50% have it and 50% don't have it. If you don't have it, you can contact us. We can put an air preheating system in your cracking furnace and improve the efficiency. Well, thank you for your response. Typically, the modern furnaces or the current design or most of the ethylene furnaces have this design which has been used in the industry for last 30-40 years, which is pretty much like they build furnaces in a pair. So there are two furnaces. This is the radiant section over here. Then we have an offset convection, and this is the offset convection of the other furnace and second radiant section. So they are built in pairs. We have the coil in the center. Vertical coils are used in the center. Then we have a transfer line exchanger on top and steam drum on the top of the furnace, and ID fan and stack right on the top. So this is a furnace design which has been popular for last 50 years, I would say. Most of the furnaces are built like that, whether they are 50,000 tons per annum or 200,000 tons per annum. And it is kind of modularized. There are different firing patterns. People earlier used to install sidewall burners, but the trend has gone more towards floor burners now. And modern designs even have SCR built into the convection section for NOx reduction. So when we talk of ethylene cracking furnaces, which side controls the heat transfer? Is it the process side? Is it the flue gas side? Or is it both process and flue gas side? So most of you got it right, majority got it right. In all fired heaters, not just cracking fired heaters, it is the flue gas side which is controlling the heat transfer. And that is why the flue gas becomes very, very important. The fuel becomes very important. The burners become important. The convection section becomes important, because that's where the heat transfer is being controlled. And the reason flue gas is controlling is it is the heat transfer coefficient, the side which has a lower heat transfer coefficient, controls the heat transfer overall. So flue gas side heat transfer coefficients are much lower as compared to the fluid side heat transfer coefficients. So that is why flue gas side is always controlling, and it's pretty important. That's why it is important. Okay, I think this is a quick question for you. Who is the licensor of your ethylene cracking furnace? Uh, so Technip and Lamas are split over here. They are the major licensors, two licensors out of four. These are the different licensors which have been offering SRT or HSC or USC, different technologies for cracking furnaces. We already covered this, typical temperatures in cracking furnaces. We already covered it, so I won't go over here. Also, we covered this also, radiant section, convection section, transfer line exchangers, ID fan and stack on the top. This is a 3D model of cracking furnace. Now, when you look at the heat duty part of it, we covered it actually. So if you look at it in any furnace, 30% of the heat duty is going into the reaction, endothermic heat of reaction. And almost 47% of the heat duty is going into preheating the feed and dilution steam to the reaction temperature. So 35% is is taking place in the convection section and 12% is taking place in the radiant section, and 16% is going into HP steam superheater in the convection section. That is basically what is going into this thing. New furnaces, typical efficiency could be anywhere between 93 to 95%. Heat loss is about anywhere between 1.5%, and stack heat losses are typically about 5%. So I think we already covered this. I will skip it. So let's move on to the combustion side, and I want to ask all of you quickly, what is heat? Is it work? Is it energy? It's power, or none of these? So I think I gave a little bit more time for this answer. Uh, well, almost all of you got it right. Heat is a form of energy which is transferred from one place to one source to other source. And here we are transferring the heat from chemical energy to heat energy in the fuel, and then that thermal energy is being transferred to the coil. So again, a quick question for you. What type of reaction is combustion reaction? Is it an endothermic reaction? Is it an exothermic reaction? Is it autocatalytic or photochemical? Well, majority got it right. It's a exothermic reaction. So this is the one which is giving out heat. Cracking reaction is an endothermic reaction which is needing heat. So combustion reaction is an exothermic reaction, gives out heat. Let's talk a little bit more about this. Is combustion happening in liquid phase, gas phase, or solid phase? So we have all three types of fuels, but hey, almost all of you got it right. Actually, I don't have to explain anything. I mean, combustion is a gas phase reaction irrespective of the type of fuel, whether you are having liquid fuel, solid fuel, or gaseous fuels. Combustion is a gas phase reaction. Thank you very much. Uh, the combustion process is usually accompanied by well, a majority of you got it right. Thank you again. Combustion process is usually accompanied by rise in temperature and pressure. That is because we are producing heat. So as a result of heat, we increase not only the temperature, but the volume of the products, the flue gas products. So it increases both temperature and pressure. Thank you. True or false? Combustion is a chemical reaction between fuel and oxygen producing heat. Some of these questions may appear very simple, but we just want to get our fundamentals correct. That's typically my approach, to make things very simple as much as possible. So everybody got it right except one. It's a chemical reaction between fuel and oxygen producing heat. So combustion requires following. So for combustion to occur, we need three things. We need fuel, we need oxygen, and we need a source of ignition or heat. We need all the three things, then only the combustion will occur. There is a parameter called minimum ignition temperature, and unless the fuel is above that temperature, it will never combust. So for that reason, that's why we have an ignition torch or pilot burners or some source which brings the temperature up, and then the combustion starts. And once the combustion starts, then it becomes self-sustaining reaction actually. So that's typically what we want to do. So what is combustion? Combustion is chemical energy stored in fuels. This energy is released in the form of heat, and we are converting chemical energy into thermal energy. And the reaction is basically between fuel and oxygen, although oxygen is derived from air. And the products of combustion are known as flue gas products. What type of reaction is combustion? Is it reversible? Can we go back? Or it is irreversible? It's an irreversible reaction. Actually, combustion reaction is an irreversible reaction. Combustion reaction is a spontaneous reaction. Reaction time is very, very fast, could be 0.1 second to 0.2, 0.5 in case of liquid fuels. But reaction is very, very fast, spontaneous reaction. Combustion fuel contains carbon, hydrogen, and very low amount of sulfur, and oxygen is coming from air. That's typically how we get it. How much oxygen is? Everybody got it right. Thank you. 21% oxygen is there. Air has 21% oxygen, 79% nitrogen. The nitrogen does not take part in reaction, and that is one reason why we want to minimize the combustion air so that we can have an efficient combustion process. What are the three main ingredients for combustion? Well, everybody got it right, fuel, oxygen, and heat. Let me, can I skip it? Let me skip some of these questions. I think we are reaching the end of our time. So I want to skip and give time to all of you to, if you guys have any questions, please send your questions to us. You know, I open the floor. You can send these questions by so somebody said he was not able to hear. I'm kind of surprised that you could not hear me. But other than that, I think I will keep on answering these questions. I have 3 questions on your feedback. If you can get back to me, does this webinar match your goals? Where did you? Well, I think there is still room for improvement. We will try to continue improve our webinar. So 50% found at acceptable, excellent, and 24%, but we will try to improve it. Was the course content clear and easy to understand? I tried to simplify things. So well, thank you very much. I think we got a good response. I think this question is kind of a repeat. Let's go. Let's go to the last question. Did I pass or fail? You know, I'm always scared. Did I do well? So how was my presentation skills? Were you able to hear me? Were you able to understand me? Was my diction clear? Thank you all. I think thanks for the good feedback. Let me see if there is any more question here. So thank you all for coming, spending your time with us, and hopefully you would have learned something. I will answer some of your questions separately. We didn't get time, but please look forward to our other webinars as well. And thanks for your participation. So I will end this presentation. Please send us your questions and get back to us. Thank you.